Hello. This is the lecture for Math 290 at Suffolk University. The course title is Financial Mathematics 1. The book we're going to use is by Valer and Daniel. The title is Mathematical Interest Theory. This is a course to prepare students for the financial mathematics exam in Society of Actuary. Chapter 1, The Growth of Money. And the first section we're going to cover is amount function and accumulation function. There are a few key concepts. Uh, well, here is one key concept, which is about the time value of money. So you need to keep in mind that money has different values at different times. And it's mainly because you can invest the money you have and you can earn interest or returns. And if you take a loan, so you're sort of borrowing money from the bank, then you need to pay interest. Now, if you hold the money, then it may lose its value due to inflation. So it's important to know that money has different values at different time. And in our course, normally the value of the money, the amount of money will be increasing. Okay, so you have say $1 now, and you invest, and you have interest, and then gradually it will increase. So for this part, we're going to introduce a very general increasing function. You may have heard some simple interest or compound interest, but this theory is pretty general. So we study general accumulation function or amount function. So some notations and languages. Capital AT is usually used to denote the balance of an account at T. So when we see account, it could be an account of investment, it could be account of borrowing. So capital AT is the amount. Capital A of zero is the principal. So one times zero, A zero in the account, that's the money you invest or the money you borrow. It's the principal. A little a of t is called accumulation function. It's assumed that the investment or the principal is $1. Okay, so this is at, little at. Capital I of t is the amount of interest, which is can be calculated by the amount function at t, amount at t minus the amount at zero, which is in principal. And the little I sub T1, T2 is the interest rate, is the effective interest rate for the time period T1 to T2. It is calculated by the little a T2, so it's the accumulation function evaluate at T2 and then minus the accumulation function at T1 divided by A of T1. When capital A of t equals A of 0, which is the principal, times little a of t, which is called proportionality, which is uh, mostly holds in Math 290. Then the interest rate, the effective interest rate, can be also expressed by capital A of t2 minus capital A of t1 divided by A of t1. I simply put this expression to this equation, and you will get a of 0 times little a of t minus a of 0 t2 actually, and a of 0 times little a of t2 T1. And then divide by capital A of 0 times little a of T1. And you cancel it out. A of 0, you would get that. When the time periods are having the same length, so you would talk about the first period, second period, and so forth. And then we can define IN, which is the interest rate at time period n, which can be found by a sub n, a of n minus a of n minus 1 divided by a of n minus 1. Okay. Let's look at examples. Simon invests $1,000 in a bank account. 6 months later, the amount in the bank account is $1,049.23. Find the amount of interest earned. The amount of interest earned is capital I. So capital I equals the amount at time t. So let's forget about copying the formula. It's the amount at time 6 months. So we will have a 1049.23 minus A of 0, which is 1,000, and that is $49.23. Find the semi-annual effective rate of interest earned. So you would have a 49.23 divided by the investment, which was 1,000, and that is 4.923%. All right, the second example, Jessica invests $5,000 on March the 1st, 2008 in an account which follows the amount function capital A of t equals 5,000, which is A of 0 times 1 plus t over 40. So this is our amount function. And t is the number of years after March the 1st, 2008. The first question, find the balance on this date. On this date, that is 4 months. Okay, so 4 out of 12. We calculate little t to be 7 out of 12. That's the number of years. So 4 months out of 12 months. And then you plug this t into the amount function, you would get this value. And I found amount of interest earned, that is this number, a of t 7 over 12 minus 5,000. That's 72.917, probably 72.92. And then the effective rate of interest during the period, that will be this number. Okay, this number divided by 5,000, 72.92 divided by 5,000. In terms of a percentage, it will be this number. And I think the answer is coming from dividing 72.917 by 5,000. That actually not very close. It's close. Um, We're not making fuss about which number we're going to use, 92 or 9917. Okay. All right, example three. Now we have the accumulation function, little a of t equals 1.03 to the 2t, t squared equal to 0. Yes. Now, if Amanda invests $5,000 at time 0, find the capital A, it's the amount function. So capital A of t equals A of 0, which is 5,000, times 1.03 to the 2t. So 2.5, so you plug in 2.5, and you calculate it out, you'll get this number. How much does Amanda need to invest at time t to accumulate $10,000 at time t equals 3? And again, it's actually amount. It's not little a, it's capital A. So capital A of 3, we know that that's $10,000. That equals A of 0 times 1.03 to the 6. Okay, 2 times t is 6. So you solve for A0. It's 10,000 divided by 1.03 to the 6. So that's A of 0. You'll get this number. All right, let's work on the simple interest. Simple interest is commonly used in reality when the time is short, like days, maybe even less than 1 day, but normally it's kind of short. So for simple interest, the accumulation function is 1 plus RT. R is the interest rate annually. T is the number of years. Capital A is the amount equals K, which is the principal, times 1 plus RT. So this is A of T, and K is the principal. And a key fact is that these two functions are linear. That's important. Linear functions for the accumulation function and the amount function. And suppose we have a time period, so 1, 2, 3, 4 with equal length. Then we can define I sub n to be, let's say, kind of a definition of I sub n. And you plug in this accumulation function. So you have 1 plus RT, R times n actually, minus 1 plus R times n minus 1, divided by A of n minus 1, so 1 plus R times n minus 1. And the numerator, you cancel out 1 plus Rn, you would get R. Okay, so you have R over this quantity. And a very important feature is that I sub n decreases with respect to n. So from a bank's point of view, the interest rate sort of is decreasing along the time, so you don't want to do that. So that's why if the simple interest usually is used for a short period of time, it's for the simplicity. Okay. All right, so let's have a look at some examples. Jack loans Jill $1,600. Jill promised that in return she will pay Jack $2,000 at the end of 4 years. To what rate of simple interest does this correspond? We're gonna follow the A of let's use capital A, but it's kind of equivalent. So A of 4 years, that equals a linear function A of 0, which is actually 1600 times 1 plus R times T, which is 4. So we know 2000 equals 1600 times 1 plus R times 4. Okay. We're talking about simple interest is normally here is the annual. That's implied when we say that. It's not effective rate for the 4-year period. Okay. So then you calculate it out. You have for sorry. You have 2000 divided by 1600 minus 1, then divide by 4, you get R. Okay. So the answer, uh, I guess I'm not going to calculate it, 6.25. All right. Again, it's annual. All right. Let's calculate the effective rate for 4 years. That is 2000 minus 1600 divided by 1600. Yeah, 4. Do that. That's 1/4, which is 25%. And uh, that's actually the same as this times 4. Okay. All right. Example 2. Antonio loans his brother Bob 2,400 for 3 years at 5% simple interest. The brothers agree that if Bob wishes to repay the loan early, he may do so. And the repayment amount will still be based on 5% simple interest. Find the amount Bob would be required to pay if he makes his repayment at the end of 3 years. Okay, so all right, so A3 after 3 years, right? That equals A0, which is 2,400 times 1 plus R, 0.05 times T, which is 3 years, and 1 plus RT, right? And that is 2,400 times 1.15. Okay. So, all right. So that is $2,760. And interest rate obviously is 5%. Okay. All right. Now, what if Bob pays back in 2 years? So in 2 years, so 2 years, 2,400 times 1 plus R, which is 0.05. times 2 is 2400 times 1.1. Okay, so that's kind of easier to calculate. So 2640. Okay, 2640. And A1, let's calculate A1. That equals 2400 times 1 plus 0.05. Okay. And it's 2400 times 1.05. All right. And you'll get three numbers. Let's work on I1, I2, and I3 if the loan lasts the full 3 years. Okay, and remember these numbers will be decreasing. Okay, so how can we do that? We can draw a simple line that illustrates the years and 1, 2, 3. So you would have 2400 at beginning, and after 1 year, I actually need the numbers. I didn't calculate out, so I'm gonna just look at these numbers. 2640. Hold on a second. Okay, so let me put it on the top. So normally I put these numbers on the bottom. And so you have a 2400, and then you have 2520, 2640, and 2760. Okay, and then you can calculate little I. I1 is 2520 minus 2400 over 2400. And I2 will be 2640 minus 2520 over 2520. And similarly, I3 will be 2760 minus 2640 divided by 2640. And the numbers are shown here. And these effective rates, okay, I1, little I1, little I2, little I3, they're effective rates. And you see the effective rates are decreasing. Okay. And Jeremy invests $1,000 into a bank account which pays simple interest with an annual rate of 7%. 9 months later, Jeremy withdraws $600 from the account, found a balance in Jeremy's account 1 year after the first deposit was made. Okay, so let's draw a timeline. And this is time 0. And 9 months, 1 year. So this is 1 year, T is 1 year. And then we have a 9 months somewhere here. So 9 months, that's about, so 9 over 12, 3/4 of a year. And originally, Jeremy invests $1,000, and then he withdraws $600. You put the negative sign, and then we're looking for the amount at time 1. And the accumulation function little a of t follows a linear function. Okay? It's 1 plus r, which is 0.07 times t. Okay. The one common mistake is that you you find 1,000 accumulation function, accumulated value of $1,000 at time one, which is this, that's no problem. And then you subtract accumulated value of the $600 from 3/4 to 4/4. That's 1/4. Okay. And the reason that this is wrong is that the accumulated value of negative $600 from this time to this time uh, is not this amount. Okay. The reason is that A of t works from starting from A of 0 here, t0 here. So the accumulated function A of t, which is linear, starting from 0. And from here, it's actually the rate will be smaller. Okay, the rate will be smaller than at the beginning, effect rate. Okay, so you cannot use A of t like starting again from you treat this as time 0. You cannot do that. So, and the correct way is you calculate the accumulated value of $1,000 at time one, which is 1,000 times 1 plus 0.07. And then you need to figure out the equivalent value of $600 at 3/4, uh, equivalent amount of this value at t equals 0. Okay. So the $600 at 3/4 is equivalent to what value at time 0? So you need to sort of discount back. We're going to talk about discount back with more details later on. So it's kind of you trying to look at some value here, and it will accumulate to $600 at time 3/4. And then use this X value to accumulate for 1 year. So this is what we are doing here. So first of all, and you do $600 divided by 1 plus 0.07 times 3/4. This is like little x, okay? The equivalent value of $600 at this time at 0, okay? Because there are 2 times. And then you accumulate to 1 year, so times 1 plus 0.07. All right, so this is the correct way of calculating. I have to say that uh, there are kind of debate about uh, how to calculate the future value, the amount at 1 year from 3/4. Okay. Okay. Uh, so when the time is less than 1 year, there are 3 ways of measuring time. Uh, One is called a exact simple interest method or actual. So you count the number of days for that period divided by the number of days in 1 year. Okay, actual over actual. But you need to be very careful with leap years. And then there's another way, it's called ordinary simple interest method or 30 360. So you treat each month as 30 days and each year has 360 days, so 30 times 12. And this is the simple formula to calculate the number of days, which is 360 times the second year minus the first year, second month minus first month, second day minus the first day. Okay. And then we have a banker's rule. Banker's rule is actual divided by, well, not actual out of 360. The banker's rule is always favors bank because you're dividing 360, not the actual days of the year. Okay, because normally you borrow money from bank, so uh, the rate will be uh, I mean, sort of number of years is slightly bigger than actual over actual. All right, so let's have a look at an example. Brad borrows $5,000 from Julie on October 14th, 1998 at 8% and agrees to repay the loan on May 7, 1999. So what's the amount Brad needs to pay? Use three methods of measuring up time. It's actual over actual. October 14th to October 31st. So you have a 17 days. And then November 30 days, December 31, and January 31, February 1999. It's not leap year, so it's 29. Actually, sorry, 28 leap year of 28. The rule of leap year, please. Let's see. I think it's 4 years as a leap year, but after uh, 100 years, no leap year anymore. I mean, no leap year for that 100th year. Okay, so you can Google search for details about how to calculate leap year. Then March 31, April 30, and May 7. Okay, so you add them up. That's 0, 205. Okay. And actual, no, no leap years, 365. So uh, the amount, we're looking for amount. So A of T equals a zero, $5,000 times 1 plus R, 0.08 times 205 over 365. Okay, so that's the first one. And the second one, we need to figure out the days following the formula. So for the second one, this is the first one. For the second one, days equals the 360 times 1999 minus 1998, that's 1. And then you plus 30 days per month, assuming each month is 30 days. And you have 5, May 5 minus October, which is 10, such a negative number. And plus 7, May 7 minus 14, so 360 minus 150 minus 7, that's 203. So A of T equals 5,000 times 1 plus 0.08, 203 over 360. Okay. And for 3, it's the banker's rule. A of T equals 5,000 times 1 plus 0.08 times the actual, which is 205, divided by 360. And you can see this number is bigger than this number, is bigger than this number. Okay, the favors banker. And the values will be here. Let's continue with the compound interest scheme. This is the normal case. the simple interest, the amount function is decreasing, sorry, it's linear and the effective rates is decreasing. So it's not fair to at least one of the two parties. And compound interest is kind of fair. We will see later on the effective rate doesn't change along the time. The accumulation function, little a's accumulation function is given by 1 plus I to the t. I is the effective annual rate, and t is the number of years. Okay, so let's look at an example. Mary invests $12,000 on January the 1st, 1995, assuming I equals 5% compounded annually. Compounding interest has later on we will know if it's compounded different than annually, then the effective rate will be different. That value annual rate is called nominal rate, but for the moment, it's compounded annually, so this is actually effective rate as well. So we have this formula of A of t equals the principal times 1 plus 0.05 to the t. This is the amount function. Um, so here is 7 years. So A of 7 equals 12,000 times 1 plus 0.05, so 1.05 to the 7. Okay, so that's this amount. You should try to use calculator, get used to your calculator when you do these problems. At what annual rate of compounded interest will $200 grow to $275 in 5 years? Uh, so looking for annual rate. Okay. Again, we have this formula, A of t equals A of 0 times 1 plus I to the t. All right, so you have 275 equals 200 times 1 plus I, which is what we are looking for, to the t, which is 5 years. And you have 275 over 200. You're going to raise the power by 1/5 or the fifth root. And then you have 1 plus I, right? So you subtract 1, you get I. So this is the formula you're going to use, and you'll find I. Normally there are how many quantities of how many variables, 4 variables in this formula. So there are 4 types of problem. You know 3 variables and you're looking for the fourth. You need to know how to solve each of these 4 types of problems. And the first one, we're looking for A of t given A0, I, and t. And this one, we're looking for I given the other 3 pieces of information. When we're looking for I, you use root function. Now we're looking for time. So how many years does it take for $200 to grow to 275 at an effective annual rate of 5%? So you still use this formula. That's T. Okay. Its effective rate is the same. Okay. So it's not compound. It's not simple interest. So it is compound interest. This problem it sort of uses the materials later on. Effect rate is constant, so it's we know actually later on we know it means the compound interest. So you use this formula. We're looking for t, right? So you have 275 equals 200 times 1 plus I, 0.05 to the t. So you have a 275 over 200 equals 1.05 to the t. To solve t, you have to use the log function. So log, let's use ln. You can use base 105, 1.05, that's okay, but ln is probably more commonly used. So let's do that. Equals t times log of 1.05. So t equals log of 275 over 200 divided by log of 1.05. Again, you're gonna get used to the calculator to use log function. All right, I think we're gonna pause here. Okay. Now I'm gonna continue the next time. Bye bye.